go to work. Let's do CO2 now. This one is fun. This one's got a little extra quirk to it. So first of all, got to find the central atom. We can look at electronegativity values, or we could just look at what it is, because I will tell you this. Any time that carbon is involved in a molecule, it will always be the central atom. Always. The other thing that kind of gives it away here is the fact that you have how many oxygens? 2 of them. So it'd be kind of weird, wouldn't it? The 2 oxygens bonded to each other and you had this funky carbon just kind of laying out, right? So central atoms could be carbon. Let's count up our valence electrons. How many in carbon?
6.
I don't think so. How many valence electrons in carbon? 4. Now, how many in oxygen? 6. And you have 2 of them, so it's 4 plus 6 plus 6 for a total of 16. I'm going to draw this one correctly, because you know what? Why not draw it correctly, for one? Let's let us not have to change our drawing. So you put C, you single bond it to an O, you single bond it to an O. How many electrons did we just use up? 4. So now we have 12. We have established this already, but is oxygen an exception? Is it one of our things that's listed? No, so it wants how many electrons? 8. So this one has 2 right now, so it needs 6 more. So 1, 2, 3, 4, 5, 6. You now have 6 left over. And 1, 2, 3, 4, 5, 6. And you're out of electrons. So now you start asking, is everybody happy? Well, the oxygens are ecstatic, right? They've got 8 electrons. Yay, octet rule fulfilled. But look at your carbon. How many electrons does your carbon have right now? Only 4. But there's no more electrons to put in the middle. This is when you end up creating multiple bonds. And here's how you do it. You take an electron pair from one of the outside atoms and you swing it in. So what ends up happening now is you end up with this. Carbon, double bonded O. Now these 2 are here now in the middle. So that leaves 4 on the outside. Now I want you to note something. Do you guys notice how I've written these on the corners now instead of on the top and in the middle? There's a reason for that. And that is because electrons are like charged. Therefore, like charged things, according to Coulomb, do what? Repel. And that's why they'll shift to try to stay away from each other. That's that whole bond angles thing, right? Is those angles are established in order to maintain Coulomb's law. Now, we still have an issue because, let's look at what happens. We made a double bond, right? Is carbon happy yet? No, it's only got what now? 6. So what do you got to do? Do it again. Make another bond. Now, inevitably, this question always gets asked to me, so I'm just going to answer it now. Mr. Gerby, can I make a triple bond and just a single bond? The answer is no. And that is because there is always a desire to be symmetric. And so what happens here is one of these lone pairs will swing in. It does not matter. I picked the top one. I could have picked this one out here. As long as I pick one of my lone pairs. Good question. And so what you end up with now is this. C double bonded O over here like we had before. But we end up getting this new double bond. O. And the oxygen, or those electrons, shift a little bit. Right? Now, is everybody happy? Yes. 1, 2, 3, 4, 5, 6, 7, 8, oxygen's happy. 1, 2, 3, 4, 5, 6, 7, 8, oxygen's happy. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. Carbon is happy. Now you just got to ask yourself about the VSEPR. So you look at carbon. How many things are bonded to the central atom? How many things? There's one oxygen here and one oxygen here. So how many things? 2. Any lone pairs? Any lone pairs on top or bottom or anywhere around? No. So you go on your chart and you find where it says 2 things, 2 which are bonded, and 0 which is lone pair. It's the very top. And so what's the shape of this molecule? It's linear. And have I written it correctly as written right here? Obviously the orange circles wouldn't be there. But is this right? Yes. The angle, 180 degrees, and the hybridization is SP. Yay! So that's multiple bonds. Let's do one more. I can do it fast. I don't even have to stop the camera, right? Because I'm not even near 10 minutes, am I?
Yeah, 6 minutes.
6 minutes. I got 2 minutes in class, so I gotta be fast. All right, let's do BCl3. So here we go. Boron, 3 valence electrons. Chlorine, 7 each, for a total of 24. Single bond, we're going to put boron in the middle. And I'm going to draw this one correctly too, because why not? So, boron, Cl, Cl, Cl. How many did I just use up?
6.
6, leaving me 18. This chlorine would want 8, so we put 6 more, right? Because 2, 4, 6, 8. This chlorine would want 2 more. 2, oh, let's not get sloppy. 6, this is now 12. 2, 4, 6. So we just use 6 more to give us 6. And 6 more. 2, 4, 6. We've placed all our electrons. Now, you start looking to see if everybody's happy. Chlorine, 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. All the chlorines are happy, but how many does boron have right now?
6.
2, 4, 6. So originally you're thinking, oh, I got to make a double bond somewhere, right? I got to swing one of these pairs, and I could have picked any of them, which we'll get to tomorrow. However, boron is a what? An exception. So therefore, will boron accept 6?
Yes.
So you got to check your VSEPR. So we got to look for 3 things, no lone pairs. So we look on here, we find 3 things, 3 bonds, no lone pairs, and it is trigonal planar. And I've written it correctly. What's the bond angles? So like this bond to that bond right there. What's the angle?
120.
Yeah, it's 120. 120 degrees. And what is the hybridization here?
SP2.
SP2. I'm not ready to assign you guys homework yet. What I'd like you to do is I'd like you to come back. This is Gerby out.